Hi, welcome back to the breadboard. About this time last year, we were looking at power supplies and DC loads, and also how to drive digital to analog converters, analog to digital converters, etc., using a Raspberry Pi and other devices. And I said way back then that we would go on to automate both the DC load and the power supply. Well, I've been working with a friend of mine, Jan Kamps from Belgium, to do just that. So what we're going to do, or what we have done so far more specifically, is we've taken this basic design that we're looking at here from way back when I posted the Raspberry Pi. I think this was back in April 2015, so almost 2 years ago, where it all started. And we've converted this control side, not the Raspberry Pi, into a design that allows us to completely either plug it into a Launchpad or via wires into a Raspberry Pi or even an Arduino. It doesn't really matter. All it requires is I2C, provides full isolation. This is going to form the basis of a control board so that we can either control a DC load or a power supply. The control board that we've chosen to automate this project is a TI Launchpad. In this particular case, it's an MSP EXP432 401R, though you could use any microcontroller because we only use 4 pins from the microcontroller itself. We're only using the plus 3.3 volts, the 2 I2C lines, which are on pin 9 and 10 of the headers, and ground. Everything else is completely isolated from the Launchpad. So as you can imagine, it will be very easy to hook this up to any other microcontroller as long as it's 3.3 volt compliant. In fact, even if it's 5 volt compliant, it doesn't matter either, because the isolator doubles up as a level converter. So the external controller can be working on 3.3, 2 point something, 5 volts, doesn't really matter. And internally, you can run it on 3.3 or 5 volts as well, completely isolated to the tune of several thousand volts. What we've included on the board here, as I've said, is the Ref 5020, which is a 2.048 voltage reference, the single channel 16-bit digital to analog converter, and a 4-channel analog to digital converter, also 16-bit. This has now been also built into a board. So this is showing one of the boards that's been assembled. You can see here, this is fully Launchpad XL compliant, but as I said, we're only using the 4 pins on this side. This one over here is just there for testing purposes. We've got the I2C lines here and a plus 3.3 volts and a ground line over here. Now there is a ground over here as well, but the reason we've used the one over this side is because this chip here is the isolating chip. So this line basically delineates the separation between your microcontroller and the analog side, which is going to go out. We've also designed the edge connector so that you can just simply plug it into a breadboard if you want to use it for experimentation. All the designs for this board are already freely available online. I'll provide the links in the post. Jan has kindly put them up. He designed the board layout for this one. As I said, he used my original DAC ADC posting, and we're using the same chips on here. And so now we both have one of these working. We've also been working on code so that we can talk to it via USB and using SCPI. Now the current code we're using is using the Texas Instruments RTOS code base under Code Composer Studio, and it's all been written in C++, but I will be providing some code that shows how to use it from a Raspberry Pi or even from an Arduino. I'll provide it as a sketch. The reason we chose SCPI is because it's a standard instrumentation protocol, and what we want to be able to do is have this be part of a lab setup where you can use something like LabVIEW to control a whole bunch of automated testing and things like that. So it will be rather cool. And you can also control it just from a simple PuTTY session as well if you want, just issuing the commands. But to help out with it, I've actually created, right now it's just a test app, so that you can drive it from Windows through the USB port too. So this is an example of the Windows IDE that we've got currently available. This is also available through GitHub if you want to look at it. All the source code is there. This is written in C# under Visual Studio 2015 Community Edition. So you can download that version of Visual Studio for free and mess around with this code if you want to, or the executable is there too. So you can just simply take it and run it if you wanted. The single channel DAC can be written to. You just put a value in here. It's just the decimal value, and you can hit set and it'll send it out. And the ADCs, you just hit refresh and it will interrogate all 4 ADCs. As you can see here, I've set 64,000, which gives a roughly 2 volt output on the DAC, and that's being read back by one of the channels of the ADC. Anyway, let's move on from here. I don't want to go into great detail about the DC load right now. I just want to give you a overview of what we're doing. So the next step, the next revision boards we did, they're basically identical except that we replaced the single channel DAC with a 4-channel DAC. Now I know this is slightly more expensive, but in the scheme of things I think it's well worth the money, because what this allows us to do is control current set points, voltage set points, and other things, because we now have the 4-channel output on the DAC. Aside from that though, it's pretty much exactly the same. Obviously we've extended this little output connector so that we can get more of the analog signals, and we've even brought out the voltage reference, so when you plug it into a breadboard or to the power boards that I'm going to show you in a second, to control the power supply or the DC load. Now I'm going to go through the DC load in a separate video. I'm just giving you an overview here to show you what we're doing, and to kick off another series of videos to show more advanced control of the DC load and the power supply. I know a lot of my viewers have been asking for ages for this, so now we're doing it, which is kind of cool. So if you followed on from the previous ones, you'll have seen this before. This was the original power supply design that I had just about a year ago, and I used a 0 to 5 volt input to this to control the set points. There was no reading back any set points back to an ADC or anything like that, and in fact in our testing on the bench I was simply using a 5 volt VREF and a pot to control the input to here. It's just a low value pot so that the 100K would not have an influence, or I was just setting it using power supply and things like that. It was not a complete power supply. So there are a few decoupling capacitors and things like that in here, and I discovered later that I had a few slight errors in the component design. For instance, the 10K here needed to be a little different. I won't go into the details right now because I will be showing you another schematic in a moment for the power supply. This is the original schematic that I came up with for the power supply. It's certainly not all my original base design. It's modeled on a similar design that I had seen from way back in the, I think, 80s from an old Agilent power supply. I have taken out a lot of the complex protection circuitry and things like that. Obviously we're not going to be spending thousands of dollars to build this. We want to make it as cheaply as possible. So this is the other part that we're going to go back and revisit so that we can control it using the new ADC board. Here is the original diagram that we had for the DC load, and I actually completed this. So if you remember, we had a nice display on it. You had a pot that you can set the current with, monitored the voltage, and you can also switch to an external control from a function generator or something like that. And it worked very, very well. And if you were watching one of my recent videos where I was testing a Phoenix Contact power supply, you'll have seen that I nicely blew the whole thing up, and I will be doing a separate video on how I fixed it, but suffice to say that I pretty much took out every piece of silicon that was inside this thing. So it was a bit of a mess. If you remember, this was the inside of the board. One of the things we want to do in this upcoming DC load is redesign the architecture of the circuit to protect itself. The question is, what have I changed on here? Well, first of all, I've completely separated the current control from the voltage control, and I've just redesigned a little bit, changing the values to work from 0 to 6 volts, 0 to 5 amps, and using a 0 to 2 volt control signal. and added some feedback. The new schematic that I've come up with is right here. Now the one you're looking at here is the current control, or the DC load control, and next to it here is the voltage control. Now if you compare the two, I will be publishing these as JPEGs and things like that, so you can have a look at them on my website and various other places. You'll find that from a layout perspective and a PCB design, they're going to be identical. All of these items that I have circled, they're going to be pads for them, but you're either going to not populate them or they'll have slightly different values. So you can see here there's 3, 6, 7, 8 components that don't get populated, and there are 4 components that have a different value between the voltage and the current. And the voltage side has a lot more decoupling. So what's going to happen here is any input noise is going to be basically bypassed right through, so the gain is going to be basically dissipated because of all the capacitors. So it should be filtering out any noise. Now the values of these have been adjusted on the voltage side so that they can support 60 volts on the input, but only give out here about 0 to 2 volts. It's actually slightly less than 2 volts. I think it's 1.98 or 1.95 or something like that. This allows us to use the 5020 and a 3.3 volt supply on our ADC DAC board, which is going to plug into here. And the other thing that I've added is I've got feedback. So let's just flip to the current one, because the DC load is the first thing that we're going to be building. And you can see here there's just less decoupling on the input. The gain is multiplying by 7.8 because we're still assuming a 50 milliohm current sense resistor. I've added a diode forward biased across the sense resistor to limit the voltage to about 600 millivolts across this if anything happens with this MOSFET. One of the things that happened before, that when I blew up my power stage of my current manual DC load, is I had 30 volts on here with a power supply that was able to supply 10 amps under normal load, and was able to, for a very brief period of time, supply up to 60 amps. So even just 5 amps, which was the limit of this, at 30 volts was 150 watts. And that was more than what this could handle. The MOSFET basically failed. It took out the current sense resistor, and what happened then was that the 30 volts was fed back through. And if you remember on the original design, there's only 100 from the gate of the MOSFET, there's only 100 ohms going back into the op amp. And even from here, which is where, when this went open circuit, you've got 30 odd volts here, so therefore you had 30 volts through a 1k ohm resistor, which would give you about 30 milliamps went into the op amp. And these gates, the inputs to the op amps, usually by design can only tolerate about 10 milliamps max through the protection diodes that are on these inputs, either above or below the rails. They'll start to conduct, and we went to 30 milliamps, so it was like 3 times more than it was able to handle, and it basically took it out. So what I've done here is every single input to an op amp has a 100k resistor in it, so that even if you had 100 volts here, it would only be 1 milliamp flowing in here, which is well within the current capacity of the op amp for protection. The sensing here will either connect to the current sense in this case, or if you were using a power supply, it would, so another exact same board would connect to the output volts so that you can measure the output volts. And of course the, obviously the feedback would be different. This is multiplying because it's measuring current. In the case of the voltage side, it's going to be dividing because it's measuring voltage, so it's 0.033 is the gain to take it down to that 2 volts on the output. What we've also added on the DC load perspective, and this is the same for the current, is we've kept the integrators that we were using on the power supply project to drive the MOSFET. Now what that allows us to do is have a controlled response where the set point is slightly out from the actual measured voltage, and the integrator will creep it up in a controlled fashion to bring it to that set point. Now, the way that this works as well, which is slightly different, is on the original DC load, if there was no control signal coming from the op amp, the MOSFET would be turned off. It would need something to pull it high. In the case of the schematic that we have here, the MOSFET is going to be pulled high permanently through a Zener diode. Now, the 6-volt one might be reduced to about 3 volts and a 10K pull-up, and that's going to hold it on, and the op amps are going to be able to pull it low to turn it off. So it's a little bit reversed from what we were doing before, but I think this allows us to have a lot more flexibility in the control of this system. Now, I wanted to have a single supply to run this separate to the power input, which in the case of a DC load would be connecting up here and going back out on the V-in down here. So I've designed it to use just a 12-volt supply. So there's a 5-volt regulator, which is going to upfeed to the analog to digital, digital to analog converter board, because it needs a supply that's based on not using the supply from the Launchpad or the whatever controller you're using. If you didn't want the isolation, you could just jumper it across. It wouldn't hurt it. But in this case, we're keeping the isolation. So we're sending 5 volts up there to drive all of the analog circuitry on that converter board. And we've got the set point coming in from it, controlling the integrator summing point that goes in the integrator, comparing it to the set point current. It's going to give a lot more dynamic feedback. And of course, with the decoupling capacitors, it's going to give a faster response to transient changes in the set points, for instance. And one of the changes on the MOSFET side is I've reduced the direct MOSFET resistor to 100 ohms, and I have a 5K with a 0.1 microfarad capacitor in parallel with it to the drive. So if there's a quick change in set point, the capacitor would effectively bypass the 5K resistor, allowing the set point to be pulled down quickly, but then the resistor would discharge the capacitor back through, allowing it to go back to a steady state. And if you want to add 2 boards together, so you're doing a power supply, you would use the voltage converter board, and these pins here that say extender, you would connect them, just jumper them across to this board, extender pins 2, so that the op amps from the other side can pull down the same MOSFET. The other benefit of this design is if you wanted to have 2 MOSFETs, you could put them in and you would just have one gate source from one board going to one MOSFET, the other gate source on the other board going to the other MOSFET. So they would be driven through their own 5K, 0.1 mic, and 100 ohm resistors, but they would have a common point that would allow them to work in parallel. And I think, I haven't tried this yet in this configuration, but I think that should work pretty well. Because we've got these op amps and I want to be able to get to true 0 volts, we need a negative supply for these op amps. The original DC load didn't have that, so you could get very, very close to 0, but never quite exactly 0. So what I have is the 12 volt coming in. We've already got the 5 volt regulator, which is running for the external supplies. It's actually not used for anything on here, but it's a really low cost component. But we have this LM2662, which is a capacitive voltage converter, and what this is going to do for us is it's going to invert the 5 volts to a negative 5 volts so that we can drive these op amps. It can supply maybe 100 milliamps or thereabouts, but that's more than enough just for a single op amp, and these are not expensive. So I put one on the board to provide the negative rail. It means that supply, if you're doing this as a DC load, can just be from a little 12 volt wall wart that you could just feed in. I haven't put the decoupling capacitors on the diagram here just to keep it a little simpler, but the actual board layout, once I do one, will have decoupling capacitors for the power supply and the op amps and things as well. If we go back and look at the original power supply design, where is it? Here, you'll see that I'm using 2 op amps for the current, 2 op amps for the voltage. There's no feedback for the actual of the current or the voltage, so I've had to add that, and I wanted to allow it to be scaled if you wanted to, depending on how you're going to do the feedback. I also needed to be able to measure the raw voltage of, in the case of a power supply, of the actual high voltage side of the power supply, and I also wanted to be able to measure the temperature of the heatsink. Is I've added a thermistor, which is just driven from the plus 5 volts through a 10K. So I've added a feedback. It's a 1-to-1 gain. The reason for that is because the sensing is effectively reversed. So when you start having, in this case, current flowing, the output of this starts going negative. It's only going to go to negative 2 volts roughly, even for 5 amps going through the current sense resistor, because that's the way that I've set this up. But of course the ADCs can't read negative voltages, so I'm just using the spare op amp on this side to flip it back to positive again. So that's why it's got a gain of 1. If you wanted to drive a meter, like a display meter or something like that, and you needed a different scale, all you have to do within the limitations of the 12 volt supply, because these are running on plus 12 and minus 5, is change the gain ratio of this, and you could then make it whatever you wanted it to be. The other op amp down here, which is also new, is simply being used to detect the raw voltage that's either being fed into the power supply or that is being provided by whatever you're loading if you're using this as a DC load. So we've got the sensing of the raw voltage, which is also what we need for the DC load. We've got the drive to the MOSFET, we've got an extender that can go to other boards, and we have our DC input to drive all of this, and then we've got our temperature sensing, and that's pretty much it. I think that's everything that we've covered. This power stage, by the way, is shown on both diagrams, but it's not two separate MOSFETs or anything like that. This one is basically the same thing that both boards would be connected to. You would just connect them slightly differently, and we'll deal with that when I do the video that actually shows how these are all going to work. The first thing I'm going to do is build up this current version on a breadboard so that I can validate the entire design. The op amp, I'm going to use a precision zero offset, zero drift kind of instrumentation amplifier. They're in high quantities, they're like $2 or $3 each, so it might cost $5 or $6. But because of the layout of these op amps, the pinouts are exactly the same for a huge range of them. So because we're only using minus 5 and plus 12 volts, almost any generic op amp will work here. The same as all the resistor values. I've picked values that are off-the-shelf standard values, even on a 5% E24 range of resistors. All of these values should be able to be gotten easily. So if budget is a concern, you can just use cheaper 5% resistors and it will still work. It won't be as accurate, of course. So if you just want a crude DC load, then you can just put 5% resistors in here. If you want to have something that is going to be very, very precise and not require much, let's say, software calibration, then put 0.1% resistors in a lot of places. Now, the only ones that really matter for the 0.1% are really the ones that are involved in not the integrator, so only the two sensing. So basically the input from this sense, that's really the only one that matters from a precision perspective. I'm either going to use KiCad or I'm going to use Eagle, both free software circuit board design tools, and I'm going to make a little board. So I'll get some made for myself. If you want some, they're very, very cheap to get made now using a lot of the online services. I'm not going to be selling them or anything like that, but the files to make them will be put out on OshPark and other places, so you can just pick it and get some of your own made if you do choose to follow on with this. It's a work in progress. As we build the new board and we get this working, we're going to be enhancing the code that's going to be running on the Launchpad. Now, as I said, this is using Code Composer Studio, and it is using the RTOS for a Launchpad, so it's very specific to that platform. But when you look at the C#, the C++ code, it will be very easy to be converted to using a sketch. So that would lend itself to using on a Raspberry Pi, on a Arduino, or on an ESP8266 or anything else you wanted to use it for. The other thing that the basic control has is that it has the capability to run on a 430 boost sharp 96 display. So this is, as I said, ultra low, just plugs on the top of the board, and we're just outputting the ADC values on here and telling you the mode that it's in. We're just doing, between Jan, Kamps, and myself, whatever we feel is appropriate for what we're trying to do. But we are making everything available so that you can hack it and slash it to whatever you want it to be for yourself if you want to build one. Anyway, that's it for now. I've wanted to keep this short, and it's already half an hour. So I will be doing the next video with the DC load itself, specifically driving it using the D2A A to D board on a breadboard, so that we can test out half of the power supply circuit, which is going to be the DC load part of it, and configured as the DC load. And we'll go into more details of that in that video. So anyway, I hope you like this. I hope you are happy now that I'm getting back on with the DC load and the power supply. I know a few of you have been asking when that's going to come back and get some more work done to move it forward to full automation. So I think you'll agree that based on what I've just told you, it's going to be quite interesting, and it's going to be a fully instrumented project and product once you're done. So I will see you on the next video. Anyway, have fun. See you then. Bye.